In this part, I want to introduce to you the use of the when we need to use the capacitor or inductor as our element, and because the conductor and the capacitor and the inductor, they have different characteristics. So we introduce a new word called impedance, and I believe I introduced the something about the capacitor before, but in this recording, I just want you to know how to use the capacitor and the inductor in the circuit. So first we use in impedance, and in the past we have resistance, right? But resistance only refers to the use of the resistors. But when we have a capacitor and an inductor involved, and we need to use the other representation of the numbers to calculate the impedance. Well, actually, impedance is something like a resistance, but just that it has the imaginary part. And I believe that some of you have, should be all of you know the complex number. And if you don't know what is complex number, you can go to the wiki and try to find more material to read. And if you still have the problem, you can ask in the class. I can delay my progress of the class and try to explain to you the use of the complex number. And the complex number is that we just represent a number in a two-dimensional way, and the one is the real, the other one is imaginary. So a new number z contains two parts. The x is the real part, and y we call the imaginary part. Imaginary parts. And if you draw it in a complex number plane, you will know the x-axis will be the real part and the y-axis is the imaginary part. So we can find a point. We can find a point z here. This one actually represents a number, okay? And unlike if you only have the real part, if you have only the real part, then all the number will appear in the x-axis. Okay, but since now we have the imaginary part y, so the way to represent the number become there are two numbers, or usually we call two tuples, and we have x and y. And why we need a complex number? Because the impedance, or you may say the resistance in the imaginary part of the capacitor can be represented by 1 over j omega c. The omega is 2 pi f. C is the value of the capacitor in farad. Okay, I will try to explain to you and derive this in my next lecture, but just first let you know. So as you know, the impedance of C, okay, will be a function of omega, or you may say it's a function of the frequency. Okay, meaning that is resistance, or the resistance in terms of the imaginary part with impedance will change according to the frequency it operates. So first, we know this. For the inductor, okay, the impedance will be j omega L. So as you can see, for j omega c, 1 over j omega c, you will see that this one will goes to 0 if omega goes to infinity. But this one will go to infinity if omega go to 0. Meaning that in very high frequency, okay, the resistance in the imaginary part or the impedance will become very small. It's something like a resistor. If the resistor value is high, then the current flow through the resistor will be small. Same thing, if the resistor value is low, then the current flow through it will be high, okay, under the same applied voltage or the same signal. So the impedance of a capacitor means that if you have very high frequency, okay, then its value is small. It's something like a short circuit. But on the contrary, if you have the omega which is close to 0, then the impedance will go to infinity. Then it's something like an open. Okay, open means that you have very, very large or infinite abilities to stop the current flow through this element. Okay, so this is the capacitor. So it's quite different from the resistor, right? Yeah. Okay. What about the inductor? What about the inductor? The inductor is j omega L. The inductor is j omega L. So it acts very different or in the opposite way of a capacitor. This one will go to 0 if omega goes to 0. This one goes to infinity if omega goes to infinity. So that means in DC conditions, okay, the inductor open like a short circuit. But in AC or very high frequency condition, then it's open. Sorry, it's not short, it's open. Okay, so this is the characteristic of the capacitor inductor. Okay, so the capacitor and the inductor, the impedances of the capacitor and inductor, actually they are function of the frequency. So it's no longer a fixed number, unlike resistors. Resistor, no matter what frequency you operate, it basically remains the same. So how to calculate? Since we are talking about the filters, okay, last time we talked about the filters, we need to find out how to use the capacitor and the inductor as the element of filter. As you know, the value of the value of the impedance of the capacitor and the inductor, they varies with respect to the frequency. And we apply this kind of property to design the filter. And let me first show you this one, the left-hand side one, okay. For example, this is our input. And we want to know what about the output here. So the output, okay, we call the V out. Okay. And based on the basic circuit design, we know the V out, okay, will be equal to the impedance of the capacitor. The impedance of the capacitor will be J omega C, 1 over J omega C, plus the R load, right? Load is R load. And the numerator will be RL, right? So if we try to this way we can multiply j omega c to the numerator and the denominator. So it will be RL, we have the j here, we have omega c here, and we have 1 and plus j RLC here, right? Okay, so as we can see, if if omega goes very high, goes to infinity, then we can neglect this one. And V, oh no, here we still have to write V in here, V in here. So if omega goes to infinity, then we know that the V out will be equal to V in, right? But on the contrary, if omega goes to 0, then V out, because omega go to 0, because this go to 0 and this go to 0, and we have 1 here, so the V out will be equal to 0. So as we can see, the frequency response, as we stated before, what is the frequency response? This is the frequency response, or this one. Okay, we talk about the magnitude only, okay, or this one. So we'll see when frequency goes very big, okay, is VI. But when frequency goes to nearly 0, we have 0. So this will be a characteristic of, approximately the characteristic of your filter. So as we can see, this one will be the high pass filter, right? High pass filter. So the gain, what about the gain? Let's go to the other side so that we can make some calculation there. As we can see, okay, the V out will be equal to J omega R C and the 1 plus J omega R C to the V in. So that means the gain will be equal to J omega R C 1 plus J omega R C, right? Okay, and let's try. We of course we already know it's a high pass filter, right? But the most important thing is to find out first what is the cutoff frequency. We call this one the cutoff frequency, as we stated before. And then the order. Okay, so first let's find out the cutoff frequency. And then we have to calculate what? We have to calculate the A, right? The A. And where is the cutoff frequency? The cutoff frequency means that the voltage at the VR at cutoff frequency should be the V in multiplied by 1 over square root of 2, right? Okay, this is the one. So this is the cutoff frequency. So if J omega C RC will be equal to J1, meaning that the omega RC will be equal to 1, then the A will become 1 over 1 plus J, right? And so the magnitude of the A will be equal to 1 over 1 square plus 1 square will be 1 over square root of 2. So the cutoff frequency happens when omega RC will be equal to 1. Okay? So if R, for example, is equal to 100 ohm, then the omega RC and the capacitor will be equal to, for example, 10 microfarad, right? Then the omega C will be equal to omega multiplied by 100 and multiplied by 10, multiplied by 10 to the minus 6. And this one will be 1. And the 2 pi f multiplied by 100, 10, and on the minus 6 will be equal to 1, right? And then what about the f? The f will be equal to this is we can make some here, minus 3 here, so it will be 1000 divided by 2 pi, which should be equal to 6.28. So this one will be approximately what? Let me do some calculation. 6.28, and we have 1, 6.28. What would be 2? Would be 7. Would be 3. And then we have 5 or 6. So it should be around 16 hertz. Around 16 hertz. So this 16 hertz. So the FC here will be around 16 hertz. Okay. Then we can try to calculate in further. We have the A. Let me rewrite it. A will be equal to J omega C. J omega RC. 1 plus J omega RC. Right? Okay. So let's try to find out the order. Although the way to decide the order is very important, very simple, but I would like to show you how to see it this way. So for example, at 16 hertz, A will be equal to 1, J1, sorry, here, sorry, I make a mistake here, it should be J here. This one will be equal to J, right, and 1 plus J, right. But because already we already know how much is the RC, okay. The RC is this one. 10 to the minus 3. So this should be omega multiplied 10 to the minus 3 here, right? Which also, this is omega is 10 to the minus 3 here. But when it is at 16 hertz, it should be J 1 plus J, right? Okay, this is the one here. So I can just write it here. We have J. We have this one. It should be 2 pi 16 10 to the minus 3, and 1 plus J 2 pi 16 1 by 10 to the minus 3, right? So because this one is a high pass filter, then we want to know how much the gain will change when it becomes only 1.6 hertz. High pass filter want to go to the lower side. So at 1.6 hertz, how much will be that? Which this one will be equal to A. And because now, because 16, 2 pi 16 10 to the minus 3 will be equal to not minus 3, sorry. Let me see if I make some mistake. This should be 160 hertz, 160 hertz. Sorry, I make a mistake here. So it'll be 160 hertz here. So this one's 160. Sorry, I'm O. So 160 here. And we know, so we know 2 pi multiplied by 160 multiplied by 10 to the minus 3 is approximately equal to 1, right? And what about, as we know, we want to know how many dB off per decade, right? So we should be right here, we should have 16 hertz. This should be 160 hertz. And now we have 16 hertz. What about 16 hertz? Okay. Right. For the 16 hertz, we see this one will be equal to J to the 2 pi multiplied by 16 multiplied by 10 to the minus 3. This one will be 1 plus J 2 pi 16 10 to the minus 3, right? And we know, since we know this one is approximately equal to 1, then of course this one will be J multiplied by 0.1. This one will be equal to 1 plus J multiplied equal to 1 here, right? And how much will be that? How much will be that? This one will be, if so, A 160 hertz will be equal to 0.1, right? Square, absolute value of that, 1 square plus 0.1 square, right? And we know this is 0.1, and 1 plus 0.01 square, and I say this will be approximately 0.1 divided by 1, and which will be 0.1. Okay, and then we know that V out will be 0.1 multiplied by V1, right? V in, and which we have, how much was that? Then we can calculate dB, 120 by 20 multiplied by base 10 log, and the V out over V1, which will be 20 log 10.1, will be approximately minus 20 dB. Okay, so we goes from 160 hertz to 116 hertz, which is a decade, right? But the amplification goes from minus 3 dB to minus 20 dB. So it's around minus 20 dB per decade. So this one will be a first order high pass filter. First order high pass filter. Okay. All right. Because we make some change here, so that's why it's all in 0.1. Otherwise, it would be 0.09 something. Okay. So this one is a high pass filter, first order, and the cutoff frequency should be 160 hertz. Okay, and this part, we want to find this part, which is 16 hertz. Okay, so this is the way to calculate it. Okay, so we can calculate the frequency response of the filter. And same thing to the other one. For example, same thing to this one. Okay, we have this one from the right hand side, and this is the filter. Okay, for example, this one is a 100 millihenry, the 200, and we have 1K here, and then I can also write the function similar to the one I write for the capacitor. So let me rewrite this one to the handwriting note. Okay, let me memorize it. 200, 100 million, 1K. So for this one, let me redraw the circuit. The circuit will be 200 ohm. We have capacitor here, we have inductor here, 100 millihenry here. We have 1K here. And this is V in. This will be the V out. Okay, this is just write V0. That's enough. So we can in parallel of the two, in parallel of these two elements, right? These two elements. I first make sure that my writing is correct. 200, right? Okay, these two are in parallel. So let me first write the function here. And this one we have a j omega L here, right? So we first in parallel, then this one will be 1K, the 10 to the 3, multiplied by the j omega L, and the denominator will be equal to 10(3) plus j omega L, right? This will be this one, okay? And the overall, then the V out will be equal to 10 to the 3 multiplied by j omega L, and 10 to the 3 plus j omega L, and the denominator will be 200 multiplied by the 10 to the 3 plus j omega L, the 10 to the 3 multiplied by j omega L, right? And if we multiply the 10 to the 3 plus j omega L, we have in here, and we will have 10 to the 3 multiplied by the j omega L, right? Okay, and we do the multiplication first. We have 2 multiplied 10 to the 5 plus 200 multiplied by j to the omega L, right? And plus 10 to the 3 multiplied by j omega L here, right? And let's try to do some arithmetic. J omega L, we have 2 multiplied 10 to the 5 plus this one will be 1200 multiplied j omega L. And let's try to do some thing that I can, that this is 10, it's 100. This will be 2 to the 10 to the 3, right? Okay, and if I I try to bring in the 200 milliampere. Oh, this one was 200 minus 3 here. And we have a 3 plus 12 plus G, and the omega, and 200 minus 3 here. Okay. And again, we can do some tricks here where this one will be taken away, right? And this one will be 10 to the minus 1. Okay. And we can eliminate the 2 here, the 2 here. So this one finally become 10, 3 plus J omega, J omega multiplied by 1.2. And the denominator will become J omega. Okay. And as we can see, this is the A. When omega goes to infinity, right? And when omega goes to infinity, so this term will no longer important, right? So what we will have, when omega goes to the infinity, then we have the gain that will be J omega over J omega 1.2, which will be approximately, how much is that? It will be about 8, 0.8. Okay. But when omega goes to 0, what about the A? When the omega goes to 0, A goes to 0, right? So again, this one is a high pass filter again, as we can see here. This one here. And when omega goes to infinity, so this is 0.8, and then it drops to 0. That will be this one. Okay. And because there's only one inductor here, so again, this one is the first. It's very easy. This first order. When there's only one inductor or one capacitor inside here, there's got to be a first order one. So it should be a minus 20 dB per decade. Okay, and this is 0.8. So the point of the cutoff frequency, this one will be the cutoff frequency, should be 0.8 divided by square root of 2. Okay, so I will let you to calculate the frequency omega. So please, you can find it here. So same thing, we have two different kind of circuit. We have two different kind of circuit, but both of them are high pass filter. And as you can see here, the capacitor is in series with the load, right? So when frequency goes very high, then the capacitor becomes a short circuit. So all the voltage drop will drop here, right? So that's why it's a high pass filter. But for this circuit, when frequency goes to infinity, then it like the inductor acts like an open circuit. So it is like when it's like an open circuit, so the inductor can be ignored here. So all the load will be appear here, except that we have the 200 arm here, so that's why we have a drop, a little bit drop, but the drop is not much, 1.2, right? So around 0.8. So this one is also a high pass filter. So if you want to have a high pass filter, you can have the capacitor in series with the load, or you can have the inductor in parallel with the load. I think that would do. So please try to calculate this by yourself. So what about we switch this one to this one? Okay, which I will show you later. I will first like you to review all the things, and I will show you how to calculate that, and we will go through the material such that we can use operation amplifier to act as our active filter design.